So next up are Morgan and Jonathan, and they will be talking about some really exciting stuff. So Morgan will be talking about some exciting stuff that happened at the Open Compute project. Regarding the Open Compute project, some really exciting hardware stuff. And after that, there will be a recap of what happened at Facebook with open source firmware in general. So really generalized overview and some news about what's really happening. So we're going to get some insights. So yeah, let's fire it up and have a big round of applause for Morgan and Jonathan.
Hi, everyone. My name is Morgan. I am a Python engineer and responsible for the Open System Firmware project in WinWin. And now I'm talking about the dialog path ordering and building instruction for linuxboot. Here's the agenda. The first, I will talk about have a brief introduction and talk about how to have a retire order for dialog path. And next is for building process of linuxboot for dialog path. And the final is for WinWin's Open System Firmware Ready Plan from 2019 to 2021. WinWin is a cloud infrastructure provider that develops high-density computing and storage products. And we also have a rack solution for data centers. We are working with customers to enable open system firmware in our products, including linuxboot and Linux Foundation OpenBMC. Dialog path is one of WinWin's OCP server products, and it includes Intel Skylake SP processor and the RISC-BERG PCH. You can find more information on WinWin website. We have verified dialog path can be powered on with linuxboot BIOS. For retire order, you can contact JKD for the detailed information. Here's the keyboard list for dialog path. You can find the information of processor, memory, chipset, and expansion slots. We will have a demo tomorrow in Facebook. Please welcome to see it. About linuxboot on dialog path. We use linuxboot on UEFI. The framework of linuxboot on UEFI was presented last year. You can review on the YouTube. So I will give a brief overview here. The first one, extract the necessary firmware files from UEFI BIOS for initialize the platform, like initialize SPI tables. The second one, linuxboot is executed as an EFI application. So the boot flow is like the system boots from minimize UEFI and then execute linuxboot. Then the final is target OS. The following is talking about how to build a linuxboot for dialog path. First, of course, you have to download the built-in package. Second, you need to get the patch for built-in linuxboot for dialog path. I will talk about this page later. Third, build the kernel image for linuxboot. You can refer to the building guide. Fourth, place the UEFI BIOS of dialog path and base image into the building package. Fifth, start to build the linuxboot BIOS, and you can get the linuxboot BIOS at this path. Here are the notes. First, you need to configure this config to set to yes in kernel config for making linuxboot as an EFI application before building PC image. Second, the UFI of Tiago path is provided from WinWin after ordering. Third, you may also find the further information from this link. Okay, let's talk about the patch for Tiago path on the linuxboot on Tiago path. The patch is fixed two issues. The first one is UFI BIOS for Tiago path has per file as MMA compressed sections, which are not supported by the indicator Dixie core. So this core doesn't load any Dixie and SMN modules. So we need to add the parameter repack for decompressing the LCMA sections. After doing this, the Dixie core can load the modules directly. The second issue is some necessary functions are not ready, like HPI tables, PCI enumeration, but linuxboot is already loaded. This is because the lack of dependency for Linux is executed. We need to add more dependency for preventing linuxboot loaded too early. The final is for open system firmware ready plate on Kubernetes platform. In 2019, we developed the features on monolithic platform first because the Kubernetes platform is not ready yet. We would like to move these features to Kubernetes platform after we bring up the Kubernetes platform. In 2020, we would like to get these features ready, like hardware-related features, legacy BIOS functions, and OEM features. In 2021, we would like to get open system firmware ready for production. Thank you.
So thanks, Morgan and WinWin. My name is Jonathan, by the way. I'm a firmware engineer in Facebook. So WinWin, what they are doing is great. This is actually first time you can buy an off-the-shelf OCP platform from the market directly. You don't have to order hundreds of thousands like Facebook does, orders hundreds of thousands from WinWin. You can just buy one, play with it, right? And WinWin also did a lot of work that non-linuxboot works on it with just a few instructions. Download, and then you build it, and then you can run it, and then you can customize it, play with it. So that's great. So my part of the presentation will be first, give a status update. So what Facebook is doing in terms of firmware development. So Facebook is not firmware development house, right? But we are going to be one of them. So why we are doing that? And then I talk about for our stack of the firmware, what is the build system design and how we plan to enable our partners and work with the community. So getting a community, a vibrant community is vital to our success. So in Facebook right now, we are doing network server deploying. So if you remember that yesterday morning, Ron had the code, right? So that was an announcement from our networking team that they built a new switch. It's great. It's a shiny new switch. It comes with new firmware, so which runs coreboot, linuxboot, open cellular. So in OCP, there's an open cellular project. We build those open cellular devices worldwide so that billions of people can connect with each other. What's running in the open cellular devices? Coreboot, linuxboot. So they're deploying. Now, in our conference room, there are thousands of devices like this. You can play with it. You can make video calls. they run coreboot linuxboot. So we are not stopping there. We're working on computer and storage servers. So our next goal is in the data center, millions of devices in our fleet. We hope we can get coreboot and linuxboot on it. We are hacking on it. So this presentation is about what's our plan for our hacking, our design choice. So first, in the last several days, right, we heard a lot of acronyms: Slimboot, U-boot, MIM platform, and coreboot, right? But for us, we need to pick up something practical because we need to be able to get ready to get into data center in the next 1 to 2 years, and we needed to meet our users' demands, right? Our friends in our production engineering, they need to take care of millions of servers. How do they do it? How do they do it? So they have a lot of requirements to us. So in the end, we choose this solution, which we use the coreboot to do the silicon initialization. Then we put into Linux, embedded Linux kernel. And in the embedded Linux kernel, there's init run FS, have a bunch of user space tools, including bootloaders. And then from that, we use that Linux to boot the target Linux. So the embedded Linux kernel and the init run FS is on the boot around together with coreboot image. Motivation. Why do we do this? What are our requirements from our customers, the production engineering teams? So why is debuggability? So when something happens, we have to be able to debug very quickly, right? When a save issue comes, people will have to work 24 hours. Otherwise, there will be a call to the police department. So we need to be able to control our firmware. We need to be able to know the design and the implementation inside out. Manageability. Our PE team, they are all Linux gurus. They know how to manage the OS. Now they want to manage the firmware similar as they manage the OS. Workload requirement. So Linux kernel, so UEFI kernel has been great, solved a lot of problems. But over the years, we see that the Linux kernel has some more advanced designs in terms of architecture, like multiprocessor support, like for example, the interrupt support. And also the Linux drivers tend to have more attentions. So all that adds together that will meet our workload requirement better, like the fast boot time, right? If in the provisioning time, you may need to boot it several times. You do need to fast. Security. So security comes from two things. One is the more eyeballs on the code base, it would be generally be safer. Second is on the Linux side, there are a lot of security features. Innovation. So we design our own hardware, right? So when we design our own hardware, we cannot wait for somebody to develop software for us, including firmware. So once we are able to build our own firmware, we know we can crank out new firmware very quickly for new hardwares. Green. So once our hardware retired from the data center, they are still in good shape. Now people buy without firmware. What can you do, right? You can only take it apart. Now you sell hard drive, you sell some NIC card, right? But with the open source firmware, people can just download, customize, use it. Now you can sell it as a server as is. So that's the green part of it. So next part is a build system design. So here is the general build process. So we use the init run FS source. We build the init run FS binary. That together with the kernel source, we build the linuxboot payload. Now with linuxboot payload and a coreboot source and a silicon vendor binary blobs, we get the firmware image and flash on the flash, and then it boots up. So I'm going to break down into each of the components and then summarize it. So the first group of components is the build environment. So in coreboot, there's cross toolchain build for ELF. So so you need those cross GCC tools. It's downloaded from somewhere, either from internet or from your company's copy of it. You need a toolchain for other components. At this moment, it is using GCC. Coreboot using GCC at this moment, and it has some requirements. It has to be no older than 500. So those are the build environment requirements. And in order to eliminate the build environment, any potential issue brought forth by the build environment differences, we use Docker to ensure the build environment is identical. You need a FS. Our choice of the technology is Go language. So because that's for the userland code, and the Go is a modern system programming languages. It has built-in testing facilities. So we already so using the Go language, we together with the Euroot community, there is a full Go source userland with Linux bootloaders. So the Linux bootloader. So there are probably 150 or so Linux commands are rewritten in Go and runs in Euroot. We also developed Linux bootloaders. The bootloaders would have the file system drivers and the network drivers, and we'll go to the local disk and the network and the network environment to find the bootloaders and jumpstart it. Euroot, one advantage of Euroot is it can be source-based, like a per Linux. So that means that enables fast development. So when you are doing development, you can do source-based. It's like you're doing a script. But in our production environment, in our release, we use a binary like a busybox. So we build as busybox mode, unless you are working on an individual Euroot command. So this link is to the Euroot, and the Euroot has a vibrant community that it has its charters, and it has a chairing committee. In the init run FS, we also include some binaries like flash run, like DMI decode. But yeah, for example, DMI decode. Today we have it as a binary. We build it statically, and then we include it into init run FS. But we also have some interns working on translating DMI decode to Go language. So that will vastly reduce the size of the binary. Because in some of our servers, we only have 80 meg of flash. Linux kernel. You can use any stable kernel, right? For us, we use our FB kernel. The code as is. The same code as we use for the target OS. And then kconfig. You can customize the kconfig. For example, we exclude XFS support. Why? Because on our boot drive, we never use XFS. Our data drive uses XFS. But for Linux boot, it does not have to understand it, because it only needs to find the boot drive. Coreboot. Coreboot config. So it's different for each platform. So today we built 4 to 5 platforms, including QEMU. That's 4. So we have coreboot config for each platform. And when we build coreboot image, we need to add additional features. For example, like vboot. So code for vboot is outside of the coreboot Git repository. It has its own Git repository. We also need to add FSP. So to make a full firmware image, we need other SIP binary blobs, such as IFD, ME, and microcode. Put it together, you can see there are a lot of components involved, right? A lot of different things needs to be taken care of. So the bottom is the build environment, and then the linuxboot is a part that serves the entire process. It includes the build script, build configuration files, like the configurations for coreboot, the configurations for Linux kernel, and some patches. And you need to run FS. You have those things, like I have this as other banners, other Go modules. So there's like dozens actually for each of those one box. So it gets complicated quickly. So our answer to this is a build configuration file. So build configuration file included the information such as what components are included, where to get a component. You could get it from a public repo, you could get it from an internal repo, you could get it from a tarball, right? For example, let's say FSP. We give tarball to our partners, right? Because there's trade secret in it. You cannot get the source code. What snapshot is used for a component, and what's the directory structure? So we use a JSON file to capture this kind of information. And then with that build configuration file there, with appropriate build linuxboot code base, everything is built together. Configurations. So for the firmware configurations, we use the Chrome OS VPD binary blob. It already has a very good support for it. Thanks for Google's effort. So there's like a VPD tool you can run on the build machine or on the target machine. In the linuxboot, you can see that as well. It shows up in the sysfs. Configurations can be used for things like, for example, FSP configurations, right? You can set up, so ODMs can set up default configurations in VPD, and the user can set up in VPD as well, and then it can use those settings to customize FSP boot behavior. Another example is you can use the configuration to set up the boot log verbose level. Another important thing we record in the VPD is the version information. So one version is the overall version, the schematic version. We put into the read-only partition. And internal versions, what's internal versions? Internal versions is, it basically is where you get each component and with what version. So internal versions could be pretty long. It would have like 20 to 30 different components over there. You get an exact picture of how this image is built. Another cool thing about VPD is it has two partitions. One is read-only partition, another is read-write partition. So with read-only partition, once the server is shipped, gets to the user's hand, read-only partition is locked. User cannot change it. So Facebook linuxboot repo, it would include build scripts, build configurations, kernel config, coreboot config, and patches, rare cases. We will upstream it, and the build steps become 3 steps: clone the linuxboot repo, CD to it, and then build it. So this is the scenarios. Let's say the build process enables you to do what? Say, let's say, given an image, tell me how it's built, right? You send the image somewhere to somebody. The people needs to figure out how it is built. How was it built? You run the VPD tool. You get the internal version VPD variable. You get everything. Given a target, how do I debug? You boot it into user shell or OS shell. You just run the VPD command. Or you just run the flash run command, dump the image out, and then use VPD command to analyze it. Given a build information, how do I replicate the build? You clone the repo according to the build information, then you build. So in that way, we can get a reliable, replicable built throughout the process. The last agenda is how do we plan to enable our partners and support the community. So OCP is found based on the concept that open hardware will help with the industry innovation, right? So we submit the OCP platform design together with our ODMs so when we are ready to go to mass production. So we work with our ODMs on power on, EVT, DVT, PVT, and mass production. So from the firmware development viewpoint, during EVT, DVT, and PVT, we collaborate with our partner to get it ready. We get all the server features ready. We get our infrastructure ready, right? Get all the ready. Now it is ready to be mass deployed in the data center. At that time, together with ODM, we will do the OCP platform submission, and that's we called. At that time, we are about to enable the community. When we submitted the OCP platform, we submitted two things. One is hardware design spec, so anybody can just download and then using the design, either replicate the design or modify the design to suit your needs. On top of that, a new thing we are going to do is we will make the open system firmware ready. So anybody can go to internet, download the open system firmware, and then you either design the hardware by yourself or you buy the hardware, buy the off-the-shelf hardware from Win-Win in this case. After that, it's community involvement. So Facebook will be involved as a community member. In the partner collaboration phase, our philosophy is upstream only. So unless for the short amount of time, we have to stabilize our code ready for production. That's ready for EVT active, for example. At that time, we will do an internal branch. But for majority of the time, we are upstream only. So Facebook developer or partner developer, we submit a new code to the upstream repo. And the upstream repo is mirrored into internal repo. Of course, when we move our internal repo, we run rigorous tests to make sure the upstream repo changes does not regress the functionalities on our platform. And our change will immediately get pushed out to the private shared Git repo we share between Facebook and its partners. And that gets looped back to the developers. For community enablement, at the community enablement, after the community is enabled, Facebook is merely a community member. We probably will be a very active one, but we are just a community member. We are not the owner of the code anymore, but we will help to maintain all the pieces to make a firmware, to make the server to be able to power on is downloadable and redistributable. So that would include everything, including linuxboot code, coreboot code, and uroot code. And thanks for our friends, the silicon vendor binaries will also be able to be downloadable and redistributable. Then with this, OCP members can customize for their infrastructure as needed. If they need distribution support, they can get help from the community. And they can help from professional third-party BIOS vendors. Like the same thing, they get help from Red Hat, for example. All those code development will not work without a good test framework. So within Facebook, we have a lot of our own ways of doing testing, like how to get get a server, how to dispatch the test out to servers, how to connect the results. We want that to the similar process to be also available to the open source community, because we do upstream first philosophy. That means everybody's commit to coreboot, to uroot, is going to affect us. So we are developing something we call it a contest, which can run tests continuously on demand or per diff. And it will have the flexible design to have plugins to accommodate different types of test infrastructures, including our own test infrastructure and other test infrastructures of various companies. We will open source that. Call to action. So in OCP, there is an open system firmware project. Note that it's called open system firmware. It's not called open source firmware, because OCP comes from the viewpoint of open system viewpoint. OSF project, it used to be an incubation project. Now it's a formal project. So other projects would be like server project, like powers project, or thermal project. So firmware is now a very important part of OCP charter. In the OCP OSF project, we have hyperscalers, and we have silicon vendors, ARM, Intel, and there is also ODMs and other companies like IBM. So yeah, please join those and join this industry effort. And then on the open source development side, there's OSF communities, linuxboot, uroot, coreboot. Another thing you can do is buy the off-the-shelf platform and play with it. So you can play with it today. Thanks.
Thank you, Jonathan. Thank you, Morgan. About time for 7 questions. So if you have any questions, go to the microphones and ask questions. You can line up there. You don't have to stay back. You can just...
Sorry, just a quick question on the pricing for the win-win.
Morgan.
Roughly. What's the rough pricing on the win-win off-the-shelf OCP?
Price.
It's more sensitive here, so you can contact the window about the JKD.
Can you show the picture of the part numbers? Like it has several parts.
Yeah. Excuse me. 4 minutes. Here's the contact window.
Okay.
Okay.
Email.
Yes, email. This is a keep list.
Mm-hmm.
Yeah. I don't put the price on it because it is sensitive here. Yeah.
Yeah. Just to supplement what Morgan said, you can order. Of course, this is the main part, right? In addition to this, you can also order a debug card, right?
Yeah. Yes.
Yeah. And the power cable so that you can hook up to the wall, right? Because normally this just gets into rack.
Yes.
Yeah, you could go back. Yeah, this does make me really happy too, especially that debug card. It's impossible to try to find anything like that, or
yeah,
I'm afraid of electrical fires at home, so that helps me a lot. Thank you.
Okay, welcome. It also has a
That sounds great. Are there more
card.
questions?
Yeah.
Please just line up at the microphones.
Update time and boot time.
Update time, boot time means what?
Yeah, if you don't say it on the microphones, people can hear you, and it's off the record. So
Sorry, so I want to understand. Do you have any data on the boot time and the update time with this this new firmware stack?
No, we don't measure the boot time yet. You mean boot time?
I mean, once you have this core boot, how long it takes to boot, as compared to traditional boot with IA firmware?
Yeah, maybe I can explain a little bit. So first is with the win-win order at this moment, it is not coreboot plus linuxboot solution. It is minimize UEFI plus linuxboot solution. It's still a lot faster than the full stack UEFI. You may notice that they have to slow down linuxboot process to get rid of some problems.
Okay.
Yeah. So it boosts faster, but I do not have the number.
How about the update time?
Update time. You mean the firmware flash time?
Yes.
That would be exactly the same because you still flash like 32 meg of image.
But I'm sure, like, instead writing, like, you could use Linux services to write to the flash, so it's going to be much faster, I believe.
We use the flash ROM tool to flash it.
The burner.
Okay.
Yes.
It's
We use the
faster.
burner to flash the.
Yeah.
It's faster or is it same?
David, you have some ideas about speed of flash ROM compared?
want to come to the microphone and tell us something about this?
I haven't tried it on this configuration, so but since it doesn't rely on the typical SMI mechanism, the thing is it is faster on its own, but especially if you have other things going on in the background, then they won't get interrupted just because you're not going in SMI all the time.
He's a flash ROM maintainer.
So we still have time for a few questions.
So at Facebook, you did have the slide that was talking about more than just servers, and you mentioned networking devices.
Yeah.
Can you, talk about that a little bit?
Yeah. So in March of OCP, Facebook announced a new type of networking server. And in the networking server, in the control plane, the firmware is coreboot plus linuxboot. Then we are in the process of deploying this shiny new network server.
Yeah, so there's a blog post on code.fb.com, I think, called well, if you search for F16 mini pack, you'll see the announcement. The platform itself is based on it was developed in partnership with Arista, so it's actually Arista hardware, and the control plane uses a Broadwell DE. Broadwell DE.
Just ask one question about the license, right? This is a GNU license, right?
The coreboot, yeah, coreboot.
Yeah,
license.
coreboot
Yeah.
and the Linux kernel.
Yeah.
So you have your own innovation of hardware. You are giving up your patent rights when you implement something.
For OCP platform, yeah.
Okay.
Yeah. I don't know whether OCP has its own license turn or not
Okay.
in terms of hardware.
And then another thing is I see your presentation as also mentioned by Win is that a lot of features like ACPI, TPM, secure boot, UEFI, capsule update, all those things are not here. So how are you dealing with it?
Yes. So to get a new firmware into data center is not as easy as you just boot it, right? So you need to consider all the server features as you mentioned, and we also need to work out all our infrastructure tools to deal with it. And we also need to work out a manufacturing process, right? So yes, we know about that, and we have spent a lot of time, and we'll continue to spend time on this, is to figure out all the requirements. And we do have a complete analysis as far as we can get. are all the features we need to work on, and we do have a clear path toward it. Some of the things you mentioned about, yes, they are not there, but some of them are already there.
We still have time for about, I think one last question, if anyone wants to ask them something. Okay, that sounds great. Thank you, Morgan, and thank you, Jonathan. Let's have a big round of applause.
So, together with our ODMs and with the industry, we can make it happen.